Welcome to another session with me, Sri Rekha, a lecturer in mechanical engineering, Sri Rajarajeshwara Government Polytechnic, Agrahara, Sirsila. Till now we have discussed something regarding force systems. So, in that force systems, we have all discussed all the definitions of force, types of force systems, and resolution of forces, and resultant of coplanar system of forces, parallelogram law, triangle law, and polygon law, free body diagrams, Lamis theorem, conditions for equilibrium, and what is equilibrium, equilibrium of system of forces, how to find resultant by using resolution of forces methods. So now we are going to the second chapter of strength of materials for diploma students of Telangana, that is simple stresses and strains. So actually this simple stresses and strains is the first first chapter of strength of materials. Mm, but in this, so since this subject is a combination of engineering mechanics and strength of materials for diploma students of mechanical stream, so now the first chapter will be force systems and the second chapter is simple stresses and strains. So in today's topic, we are going to have an overview of this entire chapter of simple stresses and strains. So in this chapter, we are going to come across various terms such as types of forces, so types of loads, whether it is point load or UDL or UVL, based on their application, we have different types of loads that we are going to discuss. And then we are going to discuss stress. What is stress? And what is strain? And what are their natures? And what are the different types of stresses? And what are the different types of strains? And also mechanical properties of the some engineering common engineering materials we are going to discuss, like ductility, malleability, resilience, strength, hardness, creep. All those will be explained in this chapter. And thereafter, we are going to discuss something about stress strain diagram for mild steel and cast iron. So for cast iron and mild steel, we are going to discuss the Hooke's law, and because of that, based on that, we are going to draw the uh, stress strain curve, and thereafter we are going to discuss about the various problems, various formulae such as factor of safety and relation between the elastic constants. So elastic constants means modulus of elasticity, modulus of rigidity, and bulk modulus. Next, we will find stress and strain for all the bodies of uniform cross section, and for composite sections, and which are under the influence of normal forces. Where normal forces are acting, what would be the force, what would be the stress and stresses and strain developed in that composite material. And next we will be finding various formulae for thermal stresses, thermal stresses in the bodies of uniform sections. So when the uniform sections of bodies are subjected to temperature, are subjected to heat, automatically due to the change in the temperature, their body thermal stresses will be uh, evolved in that bodies. Now, so we are going to find formulae for those also, like E alpha T, E alpha delta T, L alpha delta T, and all those we are going to find. So thermal stresses and strain. Thereafter, we are going to calculate n number of problems for all these conditions, all these types of stresses and strains. So our simple stresses and strains would be concentrating mostly on basic definitions of stress, strain, and the definitions of all the elastic constants, and thereafter for in different types of material, like either it is uniform material or composite materials, what are the formula involved, and how to calculate the stresses and strains, and then what are the relations between the elastic constants, and how would we calculate all those, how would we calculate volumetric strain, etc., will be knowing in this chapter. So coming for to today's lesson, our lesson would be consisting of introduction part, then what is the load and what are the types of loads, then what is stress and what are the types of stresses, then what is strain and what are the types of strains. So these are all we are going to generally explain all this uh, in a brief manner, and from tomorrow onwards we'll be detailedly explaining each and every term and their formulae and their application of the formulae in the problems, and getting the results from those uh, in this problem, finding the solution to those problems will be done from tomorrow onwards. So, as I have told you, this chapter is going to be the first chapter of strength of materials actually. But as we have clubbed both the subjects, so we are having this as the second chapter. Now, what is strength of materials actually? So, as you know, strength is nothing but resistance of a body. Strength deals with the resistance, capacity of a body. Now, strength of materials is nothing but the resistance of the body, the maximum resistance of the body or of the material which can offer to the external applied loads. Now, this simply we can say that strength of materials is that subject which deals with the behavior of materials or behavior of the bodies under external applied forces. So again, on what factors does this strength of materials depend? So it depends upon a number of factors like type of loading. So type of loading is nothing but the weights that we are putting on the material, what kind of forces we are adding on the material, what kind of weights are laid on the material. Next, internal resistance. It is something with the internal energy of the body. Like, so if a force is applied on particular body, how much opposing force is it having? How much it can resist to that force? So that is also the factor. Again, temperature. So we have been discussing about this temperature. So if that, as you know, change in the temperature brings change in the mechanical properties of the body. The material may turn out, the hardness may decrease when you are heating the temperature, and in some cases when you are heating the temperature, the material may get melted. So when it is melting, it will suddenly change its nature from harder towards softer in nature. That is, say if it is an elastic one, it will more go it will more of going towards the plastic nature. So that is also a factor. So temperature is also a factor that will affect the strength of the material. So in material science, we we simply say the strength of material is nothing but the ability to withstand an applied stress without any failure. So, ability of the material to withstand to certain applied stresses without any failure is nothing but strength of materials in case of material science. So, in strength of materials, so this is nothing but a subject or a branch which deals with the bodies under external load. Now, this applied stress might be in various types, like it might be a tensile stress, or it might be a compressive one, or it might be a shear one. So, we know we have various types of stresses. So simply we can comprehend that this subject is that which deals with the loads, elastic and forces, elasticities and forces acting on the material. So the loads and the forces acting on the material is nothing but the strength of materials. Now this depends upon, or this relies upon, three different types of analytical methods. So whereas which can be spelled out as strength, stiffness and stability. So strength, stiffness and stability. So strength is nothing but capacity to carry certain load. Capacity to carry certain load is nothing but strength. Next, stiffness is deformation, resistance against deformation. So if some load is applied, then how long it will stay without elongating or without deforming, that is nothing but stiffness. Again, stability, it is nothing but uh, ability to maintain its configuration, means without changing its internal configuration, how far it can be able to maintain it. So strength of materials, it relies on three things. Those are strength, stiffness and stability. So this is the introduction of strength of materials. So next, we'll go for load. So as you know, load is nothing but an external force acting on a rigid body. So any external force which acts on a particular body can be read as load. So these external loads can be classified into various types based on various criteria. Now first, according to the manner, according to the manner they are applying, we have point or concentrated load. Point load or concentrated load. Next, second one is distributed load. Next, according to the nature of action, I mean how they are acted upon a body, how they are falling on a body, like with respect to time, we have static, dynamic and fluctuating or cyclic loads. Next, according to the effect produced after adding on the load, after applying the load, according to the effect produced, it means in the way it is elongating, according to the dimension in which the body is elongating, we are having uh, three types. Those are axial load, shear load and bending load. Again further, this axial load can be classified into two types. One is tensile load and other one is compressive load. So these are types of loads. So based on the manner, we have point or concentrated load. Next one is distributed load. Next, according to the nature of action, we have static, dynamic and fluctuating or cyclic load. Next, according to the effect produced, we have axial load. So again in this axial load we have two types, those are tensile load and compressive load. Next, shear load and bending load. Okay. So these are the classification. Next, let us discuss each of the load. First one, so point or concentrated load. So the load which is acting at a particular point is called as point load or concentrated load. So it is completely concentrating on particular point. It is not distributed over a region. So this is called as point load or a concentrated load. Now this load can be measured in newtons. So the load which is acting at a point is called as point load or concentrated load, and it is measured in newtons. Next is distributed load. So the load which is distributed over certain area or over certain length is nothing but distributed load. Now this load is distributed along the length of a loaded member. Say if a beam is there of 20 meters. Now a UDL will be something like, so a load of 2 kilonewton per meter is distributed over 10 meters. Then we'll consider that, so 10 meters length of the space is completely distributed by this load of 2, 2 newtons. So likewise, this load is spread to certain region. It is distributed over certain region. It is not acting at a particular point. So this is expressed in Newton per meter or Newton per meter square. So if the load is distributed along the length, it is Newton per meter. If the load is distributed along area, then it is Newton per meter square. So this distribution may be uniform or non-uniform. So if it is a uniform one, we simply call it as uniform distributed load. If it is a non-uniform one, we'll simply call it as uniform varied load. Uniform distributed load means it is equal at every cross section, at every point of the uh, area where this load is spread. So in the entire region of the load affected area, the quantity of the load is same. Uniformly, non-uniform means the load varies at point to point in the load affected area, in the distributed area. Next. So again we have a static load, dynamic load and fluctuating load. So static load is the load which is kept constant and acts on a body for long period of time is nothing but static load. So static load, we can say simply that you are putting something on a shelves. The books kept in a shelf. It is a static load. Objects placed in a house are static loads. So those are all static loads. It means those loads are applied applied up to their final value, and those are kept for long period. We are placing something on a table for longer time. That is nothing but a static load. Okay? The loads which are kept for longer period are nothing but static loads. Next comes dynamic load. So dynamic loads are nothing but the loads which are applied rapidly. These loads are varying with time to time. So something like plunger, the plunger which is heating from a flywheel. So that is a dynamic load. Next, the hammer which is hitting a wooden pile, that is also dynamic load. So it will hit the wooden pile for a few seconds, for small fraction of seconds, but it is applied very suddenly and heavily. So you can take the example of the hammer wooden which is hitting a wooden pipe is a dynamic load. Next, so axial load. So axial loads are nothing but the loads which are acting along the axis of the structural member. So axis is nothing but the axis is the center line. The loads which are acting along the center line of the material or the body is nothing but axial loads. So if these loads are acting in such a way that they are increasing the length, then it is a tensile load. Now we can take an example of a rubber. Say you're pulling the rubber out, or duster you can say. If you are pulling the duster, what happens? Its length is increasing, and similarly its area of cross section decreases, its cross sectional area decreases. So here a tension is produced, that tension is elongating the body. So we have come across this tension term even in the Lami's theorem. So if a ball is tied to a string, a roller is tied to a string, and this string is tied to a vertical wall, what happens? The a tension is produced in the thread due to the load of the ball. So it is nothing but something like elongating one. If the action of the load in such a way that the length is increased, if the body is elongated, then it is said to be a tensile load. Next, so vice versa, if I say that I am pressing a duster, so if I am pressing the duster, what happens? The length of the duster will decrease, it will shrink downwards. So something like that is nothing but it is like compressing the duster. So if the action of this load, my action of my load is nothing but, my force is nothing but to decrease its length. So if I am decreasing this length, now if this action of load is to decrease this length, then it is called as simply compressive load. Next comes shear load. So shear load as nothing but, so as you know, shearing is nothing but shear force is produced when two bodies are rubbing each other. Now, if I take an example of an IC engine, now the crankshaft in the cylinder bore will be rubbing in the crankshaft. The piston will be rubbing here and there in the engine bore. So this engine bore and the piston will be rubbing each other. What happens? Shearing is produced. Similarly, if I take any body, now the example is filing in the carpentry. After cutting the wood, we make use of wood rust files to uh, smoothen the surface. So while smoothening, what happens? This is due to the shear force of the file. The material will be removed off, or the material will be smoothened. So similarly, you also have this file is applying certain shear load to smoothen the surface. So these loads are always perpendicular to the axis of the structural member, and what it does, it will does either to cut the surface, it will simply slide over the surface and it will cut the part. It will either slide over the surface, either to cut the part or to smoothen the surface. Next, bending load. So bending load is nothing but transverse load tending to bend the structural member. Now I'll take a plastic scale, and if I'm applying say load of some 20 newtons at the center of that plastic scale, what happens with that scale which is in a plane plain manner, it will it will just start bending at the center. It will get something like U curve or C curve, U curve, like that it will go on bending. So this is nothing but bending load. So bending load is nothing but the load which will make the entire body to start bending. So that is bending load. N- Next, so stress is nothing but the resistance offered by body per unit area of cross section. So we know that when external forces act on the body will undergo certain deformation. It means either change in its dimensions of the body will occur, or any change in its shape will occur. So this changing on the dimensions or this deformation is nothing but stress. So while undergoing this deformation, it will start, this material of the body will start exerting certain internal resisting force against the deformation. So this internal resisting force per unit area is nothing but stress. So as you know, when the body is attacked by certain load, it will undergo deformation. That deformation is called strain. Now, in order to oppose this deformation, this body will give up all its internal energy, internal resistance. So that resistance is nothing but stress. Okay? The internal resistance developed per unit area is nothing but stress. Now, if I write it in a bookish language, it is simply the internal resistance or internal force per unit area of cross section is called stress. Now, for this, the symbol is sigma. The units of stress is Newton per meter square or Newton per mm square or simply Pascal. So stress is equal to, mathematically we can write it as load by area of cross section. So load, we can simply write it as load is denoted by P, so which is in newtons or kilonewtons, and A is not the entire area, will take just cross section. Now if a bar, if a circular bar we take, the cross sectional area would be circle. If a rectangular bar we take, the cross sectional area would be rectangle. Next, types of stresses. So there are many types of stresses, but as per subject point of view, we are following only three types. So they are shear tensile stress, compressive stress, and shear stress. So tensile stress is nothing but, so in we have already discussed tensile load. So tensile load is something which will elongate the body, which will increase the length of the body. Right? So when the load is tends to pull apart the particles of the material of body, causing extension in the direction of load. It is called as tensile load, and that and its corresponding stress is called tensile stress. Now, I'll let us discuss in brief. If say a bar is subjected to tensile force P, so it will be the bar will be offering a resisting force of P, equal force. Now, so for equilibrium, actually this applied force P should be equal to the resisting force. So therefore, tensile stress we can write it as sigma T is equal to resisting force by cross sectional area. So sigma T equal to PT by A. Okay. So if you are taking a body, if you are pulling that body away from each other along its axis, now its length will increase. So if the length is increasing, its area of cross section will decrease. Now this load by area will give you the tensile stress. Similarly, something opposite to it is compressive stress. So in compressive stress, what happens when load is making a body to push? Example, we have taken duster. If you are pushing on both sides the duster, what happens? The the material of the body will shorten in that direction of the load. So now this load is called as compressive load, and its corresponding stress is called as compressive stress. So this is all a compressive stress is. Now here also we can take if a bar is subjected to compressive force, say. Now the uh, the compressive stress is simply sigma C is equal to resisting force, that is nothing but the load acting, compressive load by cross sectional area, that is again PC by A. How can you find cross sectional area? Cross sectional area is simply pi by 4 d square in case of circular bar. If it is a rectangular bar, simply area is L into B. Next, shear stress. So we already discussed that shear is produced by due to the rubbing action of the forces. Okay. When the rubbing action of the forces is occurring, this shear stresses will be occurring. Now, when two bodies are uh, exerting equal and opposite forces on each other laterally and tangentially to their surface contact, then this is nothing but shear force or shear load. Now this corresponding stress is called as shear stress. Okay. So when two bodies are rubbing each other, then rubbing each other tangentially in tangential direction, then it is simply it is simply a shear stress. So this can be seen in rivets and joints. Okay. Now, so generally that section of rivets will be subjected to equal and opposite forces P tangentially. So in machine drawing also we come across this rivets. The resisting force will be shear force. So in this also Again, shear stress is equal to tangential force or shear force by shear area. Here shear area means we are not going to take the cross sectional area, but we will be taking the uh, entire area which is in contact with another body with which it is sliding. So when it is coming into contact with the other body, that region, how much region it is in contact, that one we consider. So this is shear stress. Next, strain. So what actually strain is? So strain is nothing but simply deformation. It is simply the deformation. So when a direct load is acting, when the direct load is acting on a body, then it will undergo certain deformation. So so example of tensile load, if we take, since we are applying tensile load, what happens? The body will undergo increase in its length. So this deformation, nothing but change in the length with respect to the original length, is nothing but strain. So in case of compressive stress, compressive load, what happens? It will it will simply shorten the length. So strain is a member of the deformation which is produced by the external forces. It is the deformation produced due to the external forces. It can be simply explained as the ratio of change in length to that of original length is called as strain. So it is simply the linear change in the length by original length. So it is usually denoted by small e, and see, you can see in the numerator change in length, it is in meters, and at the denominator also it is length. So you'll have no units for the strain. So mathematically you can write strain as change in length by original length. Next, so types of strains. Types of strains, if you take, so first one is tensile strain. So tensile strain, you can write it as so where does this tensile strain occur first? So we are applying tensile load. So tensile load is nothing but pulling the body away from the center. It is nothing but simply elongating the body. It is pulling away at both ends axially. If you are applying certain axial load, pull type of load, then you'll get this tensile stress. So due to the tensile stress, automatically the deformation will occur in that particular body due to the application of tensile load. So that deformation is called as tensile strain. So the deformation per unit length caused by the tensile force in its direction is nothing but tensile strain. So in case of tensile strain, it will be increase in the length. Say initially the length is L. Now after applying the load, it will be increased by value of delta L, say. Now change in length will be final length minus original length. That is final length is L plus delta L, and the original length will be small l. Now when it comes to the strain, then simply L plus delta L minus L by original length is L. So your tensile strain would be delta L by L. So that is change in length. Now let us discuss something about compressive strain. So compressive strain it itself says that when you are applying certain compressive load, the deformation that is taking place in the body which is subjected to compressive load is called as compressive strain. Now the deformation per unit length caused by the compressive force in its direction is called as compressive strain. Here, this is also denoted by E. What happens when you are applying compressive load? So its length decreases. So when its length is decreasing, automatically its area of cross section will increase. Now initially, let us say that L is the length of the bar which is subjected to compressive load. Now after applying the load, the length will decrease by delta L, say. Now the change in length is original length minus present length. So that is simply delta L. So we can write compressive strain is equal to change in length by original length. So small e is equal to delta L by L. Okay. Next comes shear strain. So shearing is occurring due to the rubbing of the material tangentially. So E is equal to when a body is subjected to equal and opposite force acting tangentially to the resisting force, the shear stresses are induced. And the corresponding strain in the body is called shear strain. It is usually denoted by phi. Phi, okay, and it is measured in radians. Now, let us take some element ABCD is subjected to the shearing stresses, okay, on both the faces AB and CD. Now, when it is rubbed, it will when a body CD, when the face CD is undergone by some shear force, what happens? This CD will displace to some other place by an angular displacement of phi, say. So this angular displacement is nothing but deformation. Now if I take shear strain, then it is measured in terms of angles in this, that is tan phi. So tan of that angle made due to deformation will give us shear strain. So tan phi is equal to shear strain. Then phi will be is equal to x by y. X is nothing but the length across the uh, x is nothing but the displacement from initial point to final point, and y is the height of that body A, B, C, D. So these are all the discussions which we have made today. So once again, let us uh, recollect. So strength of materials deals with the bodies of behavior under external loads. So it is the branch which deals with the bodies uh, uh, which are applied by certain loads. So this depends upon the various factors such as type of loading, internal resistance and temperature. Next, so type of loading. So this according to various disciplines we have various types of loads. First is according to the manner, according to the way it is imposed, we have point or concentrated load. Next we have distributed load. Next, according to the nature of action, we have static or dynamic or fluctuating or cyclic load. Next, according to the effect produced, we have axial, shear and bending. Further, this axial load is again classified into tensile load and compressive load. So point or concentrated load is nothing but if the load acting at a point is acting at a point is if the load is acting at a point, then it is called as concentrated load or a point load. So this is measured in newtons. Next, distributed load. Now, if the load is acting over area or along some length, then it is called as distributed load. It is expressed in Newton per meter if the load is carried over a length. It is called as, it is expressed in Newton per meter square if the load is acting around the area. Next, static load. It is nothing but the load which is kept constant, which is static, which is immovable one till certain time period of time is nothing but static load. Next, the loads which are rapidly moving, like a hammer on a wooden pile, we have already discussed, or something coming out of a plunger, or something like a bullet out of a that of a gun. So that will come within seconds, but it will affect. It usually affects rapidly, or it is coming suddenly within no course of time. Within very due course of time, it will hit the body and it will move away. So that is dynamic load. Next comes axial loads. Axial loads are those which are acting along the central line or center axis or longitudinally axis of the bodies. Now, if this action of the load is acting in such a way that if it is elongating, if the length is increasing, then it is called as tensile load. If this action of body is making it to decrease its length, it is called as compressive load. Next, shear load. So when two bodies are sliding over each other, then automatically due to the rubbing effect or due to the rubbing force of that particular bodies, the uh, cutting of the over the surface of the part may occur or smoothing of the surface may occur. So during this, what is happening? Shearing of the material is occurring. So this load is called as shear load. So always this load is acting perpendicular to the axis of the member. Next comes bending load. Now bending load is nothing but that transverse load. Transverse is nothing but the perpendicular load that is tending, that will make the body to bend. Its structural member is called as bending load. Next, stress. Stress is nothing but the resistance offered by a body per unit area of cross section is called stress. The resistance offered by a body per unit area of cross section is called stress. Okay. So this one mathematically can be written as stress is equal to load by area cross section, that is equal to P by A. Now units of this stress are newtons per meter square. Now stress is of three types. One is tensile stress, the other one is compressive stress, and the other one is shear stress. Now coming to the tensile stress, when this load is making that body to pull all its particles uh, away from the center line, away from the axis, it is nothing but tensile stress. If the body is subjected to elongation due to this load, it is called as tensile stress. For this, also you can write tensile stress equal to tensile load by area of cross section. Here the area of cross section is pi. If it is a circular bar, then it is pi by 4 d square. If it is a rectangular bar, then it is simply L into H. Next is compressive load. Now, if a load is making the body to shorten its length, it is nothing but compressive load. Now, the deformation that is occurring, the resistance offered in this kind of load is nothing but compressive stress. Now, compressive stress can be written as compressive load by compressive area. So, it is simply Newton per meter square. Next, shear stress. So we already discussed something that it is a tangential load which is acting perpendicular to the axis of the structural member. Now, if the stress induced in the body when subjected to that shear load is called as shear stress. Next, strain. Strain is nothing but change in length by original length. So strain is nothing but the deformation that is occurring due to the effect of load. So simply you can write it as change in length by original length. So it has no units because both are lengths. Yes. So types of strains are tensile strain, compressive strain, and shear strain. So tensile strain is nothing but when the body is subjected to tensile load, that is nothing but increasing, which is resulting in increase in the length of the body. Then, then what happens? Deformation occurs. So the deformation here is nothing but increase in the length and decrease in the area. So strain, tensile strain is nothing but change in length, that is increase in length by original length. So in case of compressive strain, it is simply what we take is compressive strain is simply decrease in the length occurs due to the compressive loading. Now this deformation here is simply decrease in the length. So this decrease in length by original length is simply compressive strain. Now we can also write compressive strain as uh, change in the decrease in the load by original load. Next, shear strain. So shear strain is measured in terms of angle. So say if two faces of a rectangular body are there, so one face is subjected to rubbing action, what happens? It will be it will be uh, it will be slided from one place to the another place. It is displaced from one region to the another region with respect to its previous height. So that angle of movement is nothing but simply it is simply you'll get tan phi. So tan phi is equal to x by y. So where x is nothing but the displacement along the x axis and y is the height of that particular body. That will give you shear strain. So these are all the topics that we have covered for today. So thank you, and tomorrow we'll discuss everything in detailed manner.